Geologists, I could never get them to wear ties or dress up, and they were always drinking beer. The engineers were at the other end of the spectrum. And so very different groups, right brain, left brain. And I'm a bipolar person, no doubt about it. I'm a right brain, left brain person. I'm a scientist sometimes, just like a geologist, and I'm looking, oh, I'm curious scientifically about that. And there's the other side of me, the engineering side, which is the side that's the clean side. The messy office is the geologist side. The clean files, I have 11,000 files here and at home. And that's my engineer side. My engineer side likes to do one thing, and that's solve problems. Put me on the problem, I'll zero in on that problem, I'll try to solve that problem. Any engineering problem out there, there's 100 different ways to fix it. There's no one way that's right. There's just the ways that you're most familiar with. Now, you're not going to make money fixing anything till you've done it about 12 times, if you're smart enough to learn from all your mistakes. So nobody comes out of the starting blocks, goes out there, and does something and makes a ton of money on it the first time out. You're lucky. You're blessed. You're walking with Jesus if you can just break even the first time out. You don't lose your shorts. How long does a general engineering contracting firm last in the United States? The average length of their life is 7 years. And that includes the guys like Guy F. Atkinson, Bechtel, the ones who've been out there 100 plus years. That's including everybody. The average time they last, 7 years. Why? Very competitive business. You make one mistake, you're done. Make one mistake on something, didn't carry this decimal over, you're off by order of magnitude, you could lose $1 million. You could lose $2 or $3 or $4 or $5 million very, very quickly. Once you lose that much money, you're not going to be able to get bonded for your next job. So it's a very unforgiving business. It's a lot of fun. It's a lot of fun to go out somewhere, see a highway or a bridge or something just gone, and they say to you, help us, do something, get this back open. And you get it back open. And you go back out there 20, 30 years later, and you see your handiwork. It's a lot better than being a parent, believe me. I got 5 kids, and none of them have turned out that good yet. But it's fun to go out there and say, I designed this. I came up with this concept. I built this in a very short period of time, and look at it. It's working. Everybody's depending on it. It's providing something for my culture, my society. It's very, very fulfilling to be a civil engineer and to do civil engineering work. And that's what my job is in the geological engineering department. I'm the geotechnical guy. I'm the civil application representative. So I'm basically a civil engineer by training. Got registered back in 1983 and got other registrations like geotechnical engineering. I have registered in geology, professional geologist, certified engineering geologist, certified hydrogeologist, all by examination. So I love taking tests. I came to Berkeley with an undergraduate degree in geology. I didn't even graduate from high school with honors. So a lot of you are here, you don't have big ACT scores. I don't care what your ACT score is. All I care is how hard you want to work. You want to work hard? That's what employers look for. We basically look for somebody who will walk in the door and say, hey, I want to work for you. You don't even have to pay me. I want to work for you. Those are the people you go, huh, really? Show me. Show how hard you want to work. What every employer is looking for is this: somebody who sees what needs doing and does it without being asked, and doesn't come up with a whole bunch of lame excuses saying, oh, wait, I didn't get training in that. Oh, I couldn't do that. You know, there's mosquitoes out there. Oh, there's muddy out there. You want me to get muddy? I mean, I don't know. I got Italian suede shoes. I don't know. I mean, those guys, send them off to structural engineering school. That's where they need to be. Okay? Structural engineers can calculate strains to 0.5%. They are engineers. They can cut it nice and fine because they're dealing with materials that come out of Pennsylvania steel mills with ASTM certifications. And I would always have conversations with structural engineers went something like this. They'd be calling me up about one of my geotechnical reports, and I'd have some clause in there saying, you know, you can expect settlement on this embankment of anywhere between 3 and 9 inches in the long term. So 6-inch variance. Structural engineer would call you up and go, hey, Rogers. Yes, sir. What is this stuff here? You know, it's about 9 inches. Is it 3 inches or 9 inches? Do you know what you're doing over there? That's a big difference. That's 300% difference. Well, sir, it's anywhere between 3 and 9 inches. Soil never settles uniformly like structures settle. It settles in a dimpled, up and down type of fashion, and the rates depend on drainage and effective stress. stress history, over-consolidation ratio, and you go on and on and on. He doesn't know what you're talking about. It's a bunch of, geotechnical gobbledygook. So finally he says, we, over here, the real engineers, structural engineering, we can calculate strains to 0.5%. What can you do? Soil mechanics, the best we can do on strains, about 150%. So if you got to do things with a lot of precision, get out of this business. This is the business that takes an enormous amount of engineering judgment and maturity. You want to be a pinhead and just run everything out of a computer to 74 decimal places, which isn't realistic and doesn't mean anything, but make you feel good. You sit down and your sphincter is nice and loose. Oh, I calculated it to 7 decimal places. Huh. Who are you fooling? Go to structural engineering. Now, rock mechanics, much worse. Rock mechanics, you're lucky to predict strains within 300%. That's on a good day with a world-class field of people. Now, why? Because we're dealing with things that were made in the ground. They are incredibly heterogeneous. They are orthotropic. Have you ever heard that word? Orthotropic. Anybody take timber design yet? Probably not. That's not sexy. Timber design is what you want to have. You're going to work in bread and butter civil engineering. Most of the structures in the world are made out of timber. Timber is orthotropic. It has different properties in all 3 axes, X, Y, Z. That's what rocks are like. Now, soils, a lot of soils are transversely anisotropic, which means they have different properties perpendicular to the bedding, but in this direction in the bedding and that direction in the bedding, they're more or less the same. Unless they were deposited in a channel, like New Orleans. New Orleans, they're orthotropic. What does that mean? That means the permeability, or hydraulic conductivity with respect to water, in old channels is super high, very, very high. It's not as high going this direction and that direction. And all the engineers down there assume it's all the same, but it's not. I had a whole bunch of professionals down there, Army guys, tell me, the peats are not pervious. Oh, do tell. Why is that? Well, because we have data showing that. Where's the data from? Oh, back in the 1960s. How much data do you have? 5 tests. What kind of tests did you do? Well, we drilled vertical holes through horizontal shale and peats, beds, silts. So right away, you're going down this direction. And then you're going to tell me what the permeability is in that direction? That doesn't work. You got the sample going the wrong way. Now, how did I get to my opinion? Oh, Festus, I'm one of those guys that sits on drill rigs. I was probably the only guy after Hurricane Katrina sitting on a drill rig who was over 50 years old, who was down there for any meaningful period of time. Everybody else drilling holes was young kids pulled from all over the country and all these different consulting companies. Now, you sit on a drill rig, you learn a lot. And you learn about behavior. We extract properties from behavior. And behavior controls everything. As we're going to learn when we get to chapter 5, we talk about rock mechanics. Differential strain is everything in rock mechanics. You don't care about stress. It's a strain that kills you. We talk about stress because it comes from solid mechanics and mechanical engineering. We love to talk about stress and calculate things to 4 decimal places. But in the real world, what you're going to be looking for with your Mark I eyeballs is evidence of strain. Things like dilation, cracks opening up, stuff like that. Okay, it's not that hard. I get down there and I'm pushing samples through this stuff, through this impermeable peats. They're impermeable. And as I'm pushing the Shelby right here, water's squirting up out of all the adjacent holes because I'm Swiss cheesing the place with holes. Now, how permeable is something if I push right here and the water squirts up 30 feet away? That's called a BAP, big-ass permeability. It's pretty permeable. Can't put a number on that one. It's way up there, above 1 centimeter per second. Yeah. And what we noticed, too, is when we're pushing it, water went higher right there and right there than it did over here and over here. So right away I see I got some anisotropy. Welcome to geology. Everything about geology is anisotropic. Now, another fundamental axiom we're going to learn today is when you are working on developing a cross-section, you can embarrass yourself, show the world how much you don't know by drawing cross-sections with rulers. There ain't no rulers in geology. The rulers are over in the civil engineering department, okay? From architecture. I like to draw everything with rulers. So if you give me 2 borings and you're drawing things with a ruler between them, all that tells me is I'm dealing with a freshman. I'm dealing with somebody who doesn't have much experience. don't you dare use a ruler. You went through my class. You go get yourself one of those flexible curves. They're nice to try on a date some night. They're nice, you know, you can measure everything. And you use a flexible curve because that's how things are in the real world. There are no straight lines in geotechnical engineering geology. Only when the lake surface. You got some lake out there that's relatively flat, but it's got chop on it too. So you don't have constant pore pressure even under a lake when you have wind blowing. So that's some of the stuff, just kind of giving you an overview. We're going to start out by doing about half this book. We're not going to do the whole book. If I do the whole book, I'm going to cram way too much stuff down your throat. That's how my schooling was. I had 10 years of schooling, and they just crammed all the stuff down my throat. And I found out pretty quick I really didn't enjoy being an undergraduate. I just had to take all these different classes. I was doing sports, I was doing military, I was flying, I was doing all these different things. I never had time to crack the books open and read the things. Only the nerds on scholarship got time to do that. I was working all the time. Didn't get to do that. So what I loved was grad school. After I went down to flight school and got out of the Marine Corps, I went to Berkeley, got to go to grad school, took 2 classes. And I'd always taken 17 to 23 units every single quarter. We were on the quarter system. So I go to Berkeley, and they say, take 2 classes. 6 units? I could actually open the book up and read the book and enjoy the class. It was a lot of fun. And I ended up staying 6 years, taking just about every class they had in the civil engineering program because my undergraduate degree is in geology. I wanted to get the depth in civil engineering so I could go take the PE exam. The PE exam is the exam that counts. That's the exam you want to go take. Now, if you, in this program in Missouri, you get double credit. They don't do that in California. Here, you actually get double credit towards PE and RG registration. California, you got to pick one or the other. So it took me many more years to get my geology registration in California because I was already a PE. So every time I would apply to take the exam, they'd say, hey, you're not a geologist. You're the enemy. You got P behind your name. Isn't that for physical education? Petroleum engineering? Oh. You're an engineer. You're the enemy. I go, what? Yeah, we don't want you taking the exam. I have an undergraduate degree in geology. Yeah, but you're practicing engineering. You're not a geologist anymore. You're a trader. You went to the other side, the dark side. Probably don't even drink beer anymore. Oh, I don't drink much beer. It makes me fat. So I drink goat's milk. Really weird. So I decided to take all these CE courses so I could pass the PE. Now, California had a real tough PE exam prior to 1976. It was very much structures-oriented. They didn't have the national exam yet. And so I minored in structures and took all these structures classes. And that's really where I learned dynamics, especially in structural modeling. If you get a chance to take structural modeling and you're going to go into earthquake work, that's the place using the strobes and the shaking tables where you actually get to see dynamics. Dynamics is impossible to teach on a static board. Dynamics is about things moving. It's like watching the babes in the bikini at the beach. I can't do that one for you on the board. It just isn't the same. Things are moving around. They're oscillating. And anyway, what I learned through all that was you're going to use everything you learn at somewhere in your career. You don't know where. The structural engineering I learned was fantastic because all of my biggest arguments that I had in my professional career were not with my clients. I'm a pretty fast-talking guy. I can make people feel good. I can tell jokes. I'm a great guy. I don't play golf, do any of those things. But the biggest arguments I had were with structural engineers, especially structural engineers designing shoring, temporary shoring, working for a contractor, usually with only an undergraduate degree and usually with one class in soil mechanics in 1947. Oh, yeah, wasn't Terzaghi, wasn't he one of those soil guys? Yeah, that's about it. And they'd be telling you what to do. And you're sitting here going, now, wait a minute. You got one course in soil mechanics. I got 37. Why are you telling me what to do? Because I was designing these things when you were a Boy Scout, and I don't like what you have to say. Yeah. You're gonna get that, especially your first few years out of college. You're going to get some of that kind of stuff. And you got to be respectful, and you got to become a teacher. And you got to try and teach the person. So one of the things that I learned to do is I have a big library of disaster pictures. That's porno for civil engineers, man. Show the disaster pictures. Look at this. Try to build a wall just like you're doing. And you can see the guys going, I don't want that. Oh, how'd that happen? Probably had a geologist in the project somewhere. Yeah, that's what it was. So you have to be able to be convincing, and you have to do it with images. We live in a visual society. So you can talk a lot about things. You can talk fast about things. You have to be able to show people, here's why I'm concerned about this. Let's walk out here and let's look at how this project performed. That was always my strongest straw. Whenever I went to work in a new area, I remember I got a job once down near Porterville. It was in the San Joaquin Valley. They don't do soil mechanics in the San Joaquin Valley. It's flat. It's all sand. I mean, what do you need soil mechanics for? That's what these guys were asking. Well, they were in a pocket of area that had expansive soils. And they didn't have the sand there. And this guy with the bank was concerned and said, we think you need a soils report because we've had a lot of problem with property casualty losses in that area. And so we want you to hire this Rogers guy down in L.A. and blah, blah, blah. I don't want to do that. You know, well, he got forced to. So, yeah, you're going up here with you have a hostile client, basically. It's like a hostile date, you know. And you go up there and just looking forward to it, you know. And I went up there, and I go up a day early. What do I want to do? I want to cruise every street around, you know, within a couple miles of where his project was going to be, and look at what? What do I want to look at as a civil engineer? Performance. Look at the street. Is it even? Does it have cracks in it? Are the cracks showing offset? We got some dandies right out here on US 63 on Bishop Avenue right here, right by the light that just showed up last spring. Settled about 3 inches. You got to go out there and look at it, nice and straight. Come back here and tell me. I'll give you $5 if you tell me what it is, because I know what it is. And it's from only 4.5 years ago. That's why you have to compact things. You don't compact things, oh, I don't need to compact. I'm only putting in this much. Great, try it. See what happens. You get a nice big crack going down the street. Now, if a truck hit that at 45, 55 miles an hour, it could cause a load shift that could cause a fatal accident. You know that if you take your transportation engineering courses. That's a real, the only reason this hasn't caused any big grief yet is it's got a stoplight right there, and it's about a 30-mile-an-hour turn. It's a tight turn on Old 66. Okay, so you go out there and you look at performance. You look at the driveways, you look at the garages, you look at all the flat work. If you're on expansive soils, you're going to see all this stuff moving around, cracking, breaking up. So the next day I meet the client out there bright and early, you know. It's a contractor, so, you know, meet him at 7 o'clock, you know, breakfast at 5 and go out at 7. It's the middle of the day for a contractor, 8 o'clock. And so you go out there, and what do? He goes out and shows me his project, and I'm very respectful. I listen to everything he has to say. And then I say, I want to show you some subdivisions over here on the same geologic materials as right here. Here's my soil map I got from the Soil Conservation Service, and I want to walk around over here. It didn't take him long to what? Pick up on how crummy everything looked. And everything looked really beat up and crummy. It did not have a nice look to it. Everything was broken. And you could see this guy going through the machinations going, I don't want a project that looks like that. There's a little bit lower socioeconomic area too. That helped. That's the kind of thing you got to do, you got to learn how to do if you're going to sell your services to your boss or to your client. You got to look for stuff like that. You got to take them out there and show the real world. I can't show them pictures of Nigeria, someplace, you know, on the side of the world. I got to show them something that's right there in their back door, right on their back door. Okay, so this is the book we're going to use. It's Perry Ron's 2nd edition, Engineering Geology. Terrible pictures in this thing. The pictures are terrible. The problems they have in it are good. That's why we use it. We're going to probably look at less than half of the book. So I want you to read the chapters I'm going to assign. And this week we're going to do Weathering of Rocks, which is Chapter 3. And Chapter 3 doesn't have any problems in the back. So I'm going to give you an assignment on weathering that's posted on Blackboard. So it's the first assignment on Blackboard under Assignments, Weathering. And then after that one, there's one on drawing a sample cross-section. So that's going to be your 2 for this week. Now, the sample cross-section, I don't want you to kill yourself. That's a real-world example from Budapest, Hungary. It's a real case. Some of you who don't have any geology background aren't going to be able to figure out the strikes and dips on the thing. But I just want you to try and do cross-hole correlation. Don't spend more than 2 hours on it, because you won't get it anyway. It's real difficult. But I want you to appreciate how difficult it is by trying to do the correlations yourself. And then I'm going to show you, after everybody turns it in, I'm going to show you the actual cross-section when they gutted the place out. I'm going to show you what they guessed ahead of time and what it turned out to be. And if that doesn't scare you, there's nothing I'm saying up here is going to scare you. But when you try to characterize weathered sites that have had a lot of weathering, there's a high degree of heterogeneity. That's college talk for things are way more messed up than you were ever led to believe in school. In school, we do everything hunky-dory, simply-dimply. That's because we got people teaching foundation engineering who've never built foundations. It'd be like going to West Point, taking a class in artillery from some clown who's never fired a cannon. But that's the system we have. Okay? So I'm going to give you real-world stuff. I'm going to show you real-world stuff. There's a high degree of heterogeneity, and you need to be designing things to account for that heterogeneity. So when you hit something you didn't expect, you don't have to change the design of the building and cause a bunch of claims, extra lawsuits, and all this kind of stuff, because that's what will happen. You know, the poop will hit the fan, and your client will not be happy with you. So we're going to start here with rock weathering, soil forming processes. And I'm going to start right here by showing you, this is Bixby Creek Bridge on California Route 1. And this is a sloping erosional surface here. And that surface is an erosional surface from when sea level was 360 feet lower than it is today. Now, off the California coast, a very dynamic coastline, it's an active tectonic margin, sea level was 360 feet lower than it is today for 90% of the last 1.6 million years. So 90% of the time, sea level was out there, much lower, and you have these very well-developed erosion surfaces. They're very, very planar. And this one, if you take the strike, you take the dip of it, and you project it, it goes offshore about 5.5 miles. And that's about right. And so if we look at that surface, this has been under subaerial weathering for a much longer period of time than areas that are like down in here, where you actually see a lot more active erosion. So this is California Route 1 north of Big Sur. If we go to some place like Panama, I've done a lot of work in Panama with the canal down there. And here we're in a tropical environment, and we have very, very active weathering processes. It's very, very humid. It's very, very warm. You're going to get more reduction reactions here in a shorter amount of time than you're going to get in a temperate climate like we have here in central Northern America. So here, it's very hard to see what's going on with the geology. Everything is covered by jungle or water or something else, and you have lots of decaying organic matter everywhere, and lots and lots of acid that is out there from decaying organic matter dissolving anything that's dissolvable. So it's a completely different environment when you go to the tropics from what you're dealing with American soil mechanics. And I just want to make that clear. So when you go working in the tropics, you forget everything you learned in Missouri and start learning some extra things, because you're going to need the extra things. My firm did a lot of work in Taiwan, Panama, and Hawaii. We did lots. We didn't have an office in Hawaii for a while because we had a lot of consultations there. Now, if we look at the soils around the earth that have formed, and this is from a book that's over 100 years old, and you look at average rainfall, the severity of the seasons, the prevailing humidity, they all exert controlling influence on the soils. And the dark areas you see here, the dark areas, like here's up in central or eastern United States, these dark areas are humid areas, areas that have high humidity. And areas of high humidity or semi-high humidity have completely different soils from areas that are more arid and semi-arid, like the Sahara or the Gobi Desert and places like that. And so western United States, you'll notice, completely different west of what? The 100th meridian. So you go west of the 100th meridian, you have calc-alkali soils. You have lots and lots of calcium and carbonate, just carbonate, calcium carbonate. All right. So pedology is soil science, the study of soils. And since 1899, soil scientists have mapped about 70,000 different kinds of soils across the United States alone, not to mention the whole world. And this was all driven by agriculture. And they're mapping the upper 4 feet. They're not going down very deep, because that's what the crops grow in. The crops and the orchards grow in the upper 4 feet. So 1.3 meters, not very deep. The superficial layer is usually dominated by organic material. We sometimes colloquially call that the topsoil unit. And it's typically leached of soluble components. Anything that's easily soluble is generally gone, unless you're in those dry areas where you have less than 20 inches of rainfall a year. That's kind of the magic number, 20. Here in Rolla, we're at 38. That's the average ISO height, average rainfall here. Underneath that zone is a layer of deposition, which we call the aerated zone. So that'd be right here. This is the aerated zone. Sometimes we refer to as the argillic B horizon, because it has argillite, it has clay formation. Clay starting to form. We call it the subsoil in classics pedology. And we call these divisions horizons. So we have A horizon up here. This is the B horizon. And then down here, we actually have a C horizon. And that's the weathered in-place material, the weathered soil, rock, bedrock. The thickness of all these depends on the prevailing weather conditions and the geomorphic setting. Geomorphic setting, what's that the big word for? Geomorphic setting is the big picture view, the geography. Are you down in a floodplain? If you're down here in the Missouri River floodplain, that's a whole different game, groundwater-wise, from being on the lust-covered, elevated uplands. They're going to be much drier, much more prone to self-drainage. You get out there on the floodplain, you don't have to drill very far to hit water, and you have very low bearing capacity, very soft, youthful soils. They just got put there 15, 20 years ago. In our case, 1993 flood. It's the last big flood around here. Most of the floodplains around here, even Big Piney Creek, are all 1993 floodplains. That's what they date from, the big year. They had a lot of flooding that year. Now, I like this, this analogy. This comes out of a physical geology text I used to use at Berkeley. And at Berkeley, we make all the civil engineers take engineering geology course. And they say, well, how can you fit that in the curriculum? They keep bringing the curriculum down. Well, Berkeley's ranked #1 in civil. So what they do, they took a 4-unit course, dropped it to 3, and then dropped it to 2. 2 units, 3 hours lecture, 3 hours lab. You don't like that? You go to MS&T. Go to Columbia. Go somewhere else. They can get away with it there. Hardest class we had in the undergraduate curriculum there was AutoCAD. AutoCAD, I think we gave them half a unit, and it was about 6 units of work, depending on how good you are at that kind of stuff. But this is a good analogy. I like good pictures, because pictures are how we teach, and pictures are how we remember things. And so if you look at this, it's saying here that soil formation is akin to what? To a drip coffee maker. Yeah, this is just what's going on in a landfill, too. In a landfill, we call this leachate. Here we call it liquid coffee, but same kind of thing. What's going on there is we're dropping water through a system, and as we drop water through a system, the soluble components, depending on their coefficients of solubility, are going to be picked up and brought down. And so as those things are picked up and brought down here, you have a solute down here that has other constituents in it. It has all the free cations are going to get pulled out of here and dragged down. And in the long run, that's why you see things here like dissolved materials are all gone and leached out, and then you'll see these nodules of carbonate are very common, which we call caliche out in the west. And of course, it's a big problem in agriculture, because as we get this progressive drying out that's occurred over the last 11,000 years, especially the last 7,000 years in North America, we get a hard pan layer down here, a hard pan of caliche. And if you don't break through that hard pan, the irrigation you do gets hung up on top of it and ends up causing fungus and rot of your roots. And so what they had to do to be able to ranch a lot of these areas west of the 100th meridian was develop giant plows, like on the Imperial Valley, southeastern California. It's in the delta of the Colorado River. They had steel plows 8 feet high. They dig down and pull up and break through that hard pan and turn it over. And then what they do, they flush the carbonate salts out. So for every gallon of water that the plant gets, they have to push 3 gallons just to wash the salts out into the Salton Sea, the Salton Sink. So that's a problem with doing agriculture in dry areas. You have to have an excess of water. It's not a real effective use of the water. Now, weathering horizons in temperate climes are typically divided into 3 basic horizons I mentioned previously. You have the A horizon up here at the top. You have the argillic rich, typically rich in clay, B horizon. Then you have the weathered bedrock horizon in C. Now, this stuff is pretty straightforward. All the problems that occur in practice, kids, are with this one. This C one is a pain in the hoo-hoo. Put that in your notes. Rogers says C horizon is a pain in the ASS. Why? Because it's so highly variable. It's worse than going to a dating service trying to find a wife. It is just highly, highly variable. So you're going to come along here, and you're going to drill a hole. Oh, this is easy, easy, easy. Oh, hit something hard. Bam, 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 bam. And get down here. Ah! We hit bedrock. So you report this in your report as bedrock. We will hit bedrock at where? Minus 23 feet 6 inches. You get out there with your subway excavation, you're 10 feet above the bedrock because you didn't drill far enough. Now, believe it or not, Missouri DOT, Department of Transportation, they have a requirement. You cannot call anything in a borehole bedrock unless you core 10 feet into it, and you get 10 feet of core out of it. You recover all 10 feet. Then you can call it bedrock, but not until then. Why do they have that standard? Because this is what Missouri looks like. That's why. Got all these weathered floaters. These are called floaters, or knockers. Knockers is not a politically correct term anymore, because Hooters took that one out of the dictionary or something. But anyway, these are called knockers, and they call them that because when the drill comes down, if he gets near the edge of them, he can actually get stuck in there. And they can be a real pain to drill through if you're not just doing diamond coring. So Missouri, we basically diamond. As soon as we hit the rock, we diamond core because there's too many unknowns trying to just auger through it. Now, go to another geology textbook, and we see the 3 dominant soil types worldwide. Now, these guys got all kinds of cousins and progeny within their respective areas. Okay, so if we go out to Washington State, we typically see something like this, a Podalfer soil. That's pretty typical. And what do we see there? We see a real nice organic-rich, humus-rich, leach soil litter on the forest floor. And then under that, we're going to get some iron and aluminum oxides that have precipitated out. You're going to get, typically it depends how much the water table fluctuates in here. If the higher the water table, the more that's going to migrate out of there by leaching. And then you get down here in the sea horizon, and this is where all the problems occur. This is where you can actually have soil around the rocks, and you can really get fooled down here. So if you're actually showing a boring in this area, and you say, oh, I hit bedrock here, you're always going to dash that contact and put a query on it. A query is a question mark. That's called covering yourself, covering your ass. You're covering your ass. You're saying, well, we drilled it, and we think the bedrock's in this vicinity, and we're going to put some mush language. And you're going to get introduced to all kinds of mush language in this course because I was the master of mush language in California. And I have that up on my website. It's called limitation of liability clauses that you're going to put on the paragraphs in your report and saying, well, this is how it was the day we drilled it, but we drilled it in the dry season. Substantial fluctuations could occur. With the passage of time, conditions can change. Groundwater is always a dangerous one because groundwater can, out here in the Mississippi River, right across the river from St. Louis, we watched the groundwater go down 3-4 meters over a period of 5, 6, 7 years. That's a lot. When you're in a big floodplain like that, you wouldn't think it would change that much. Yeah, they're out there drafting water for industrial use like crazy. So if it doesn't rain for a while, they draw the water table down. Okay, so Podalfer, pretty straightforward. That's a pretty easy one. Let's skip over here. This is not in the United States, this middle one. This is exotic stuff. Exotic. And that's more like we're going to talk about with Venezuela and Colombia. So we're going to go over here and see the desert. Yeah. So if we go to the southwest, and how far do we have to go? If we drive out Interstate 44, we go out Interstate 70, we get about halfway across Oklahoma, 2/3 of the way across Oklahoma, just west of Oklahoma City. You cross the 100th meridian, the old Chisholm Trail, and you're in dry country. You don't see any trees anymore, except the ones that have been planted by man. Things get dry. What's going on there is you got less than 20 inches of rainfall a year, so the water that's raining down is getting evaporated back out. Now, if I'm out there in western Oklahoma, how much water would I have to keep my grass green? We have something called a lysimeter test that does that. We grow grass, fescue grass, 4 to 6 inches high, and we just water it. And we keep watering it, and there's holes in this big, huge table. It's a perforated table, and the excess water is able to go out. And we measure how much water is taken up by the grass to keep it green. You want to guess how many inches to keep your grass green in western Oklahoma? 84 inches. That's higher than Shaquille O'Neal. That's up there, babe. That's a lot of water. A lot of water. So what happens here is you get all kinds of carbonate nodules, all kinds of exotic. You get sulfates. Sulfates you got to watch out for because they attack concrete and they get underneath concrete. It's a big, huge problem with pavements in Las Vegas. I have, Las Vegas. I'm going out there, every couple of months. A lot of exotic problems with soluble salts. They put asphalt in because asphalt's cheap. $4.50 square foot for 3-inch asphalt overlay. They put asphalt in, put down nice deep curbs on either side, and then it heats up to 150 degrees during the day, and then at night you get condensation of moisture underneath the pavements, and you get ettringite sulfates forming and expanding and busting the crap out of everything that's built on them. Just bust the heck out of everything. What kind of uplift pressures? 5,000 PSF. Not uncommon at all. So north side of Las Vegas is expansive soils on old Lake Las Vegas. South side of Las Vegas is old debris flow fans, lots and lots of gypsum. Gypsum's highly soluble, highly reactive, bad news stuff. So these are pedical soils, and they take a lot of experience. Very, very thin, little, discrete soil horizon. Out in the desert, your soil horizon can be little as a 1/4 inch thick. This is why we can actually get on satellite pictures, and we can see all the ruts out in the Mojave Desert from Patton's army doing maneuvers out there in 1942. Because they ran around a thing, they disturbed this very, very delicate soil horizon, and then they got condensation of moisture in the cold nights, and they got a little bit of carbonate cementation. We see that same thing in parts of the Middle East, from even Egyptian chariot wheels were made out of bronze, where they cut through and left tracks that have been weakly cemented. Now, if we look in the tropics, whoa, all bets are off. You got to think completely differently here. You got to think like you're at Starbucks and you're making very strong coffee. And you're just pouring water, hot water, through this stuff, just pouring. And the stuff's going down, and it's just picking up everything it can find, and goodbye. So all your solubles are gone. So the things that are here, what's left here? These things that look like, kidneys and filet mignons and stuff. This stuff are insolubles, bauxite, like aluminum ore. That's why bauxite comes from Venezuela, right, down near the equator. So these guys are insolubles, and these are really fun to work with. Again, highly variable conditions. One of the first building foundations I did consulting on down in Panama, we had 4 holes on 4 sides of this bank building. Couldn't correlate any of the holes. So they brought in this American consultant from New York City. You always tell a person from New York City, they're wearing all black. Because they all used to be in the undertaker business or something. They're always wearing black, Now, guy from California, how do we dress? Yeah, Tevas and a Hawaiian shirt, right? Shorts, right? Okay. I'm being nice to you. I'm wearing long pants today, okay? So Anyway, this guy from New York comes in. He goes, well, this is very easy. What you need to do is to drill a hole in the middle. And then you'll start seeing, what's going on. When I drilled the hole in the middle, it only got worse. And this guy goes, that's impossible. That's, we halved it by order of magnitude. We don't have as much distance between them. Well, the problem is you don't have a layered sedimentary system. All these things are getting there by leaching in place. And you have little percolation corridors that look like gopher holes. Some of them are going over here. Some are going over there. Some are going out the rear over here. And you try to figure that out with a two-dimensional cross-section, and guess what? You can't. You can't do it. So what do? Everybody asks me, well, what do you do, Dr. Rogers? I said, well, you draw a dash line, and you have big 2 sigma lines above it and below it. So meaning the uncertainty is very great. Now, you got to realize, the closer the borings are together, the less uncertainty. The farther the borings get apart, the more uncertainty there is with where that geologic contact goes. You got to be careful, but you got to be real aware of geotechnical uncertainty, because that's how you're going to sell your client to do more geophysical work, or to do more cone penetrometers, or do more borings. Borings are the last thing I do, folks. I mean, borings are like a Polish minesweeper. Okay, you ever seen a Polish minesweeper at work? You know what that is? Ready. Okay, this is an Army thing. That's a Polish minesweeper. You're just out there, bop, 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 and you're hoping to hell you hit something, but your chances of missing it are very, very great. I mean, borings are like little piano wires stuck around. It's very easy to miss things. All right. So if we look at that 100th meridian line, the rough 100th meridian line, it looks like this. Goes across. These are calcium-rich, calcite-rich soils out in the western part of the United States and non-calcic soils in the eastern part of the United States. And so foundation conditions are going to tend to be very different depending what side of this line you're on. Now, the problem with out west is watering. That is dry area. They don't get as much water. It's not humid. But what if you go to Phoenix, Arizona, right down here? We go to Phoenix today. There's all kinds of green things growing. Where's that water coming from? The Salt River and the Verde River and the Colorado River. So they're adding water to an area that used to be very dry. And there's a whole new area of soil mechanics, which is called unsaturated soil mechanics, where we deal with things like hydrocompression. We're going to talk about more when we get to Chapter 4. Those are issues that used to be completely missing from the geotechnical textbooks 20 years ago. They're a big issue today because in places like Phoenix and Las Vegas and Palm Springs and other parts of California, they play a huge role in damage. Now, here's a typical kind of soil you see in coastal California. Now, coastal California, every mile I go in from the coast, the soils change. It's not like around Phelps County. I'm in the most boring part geologically of the North American continent right here. This is the oldest erosional surface in North America. Over at Fort Wood, they've documented erosional surfaces over there, and up here at Rolla Airport that date back to late Middle Miocene. That's the old, it hasn't been glaciated. It's not high enough to get a lot of erosion. Just not a lot of exciting stuff has happened here, So in terms of geologic deposition and erosion. But in California, you have that rain, you have moist air in the wet season coming off the ocean, and that air bleeds off as you go inland. So you don't have to go but 20 miles inland, and you're in a sub-arid environment. You go 40 miles inland, you're in an arid environment. So, but over in San Francisco, you freeze your tush off in the summertime because you have this coastal inversion breeze coming in. It's real cold, clammy, and chilly. So here we are right here. Now, we're about 20 miles from the ocean here. We have a very, very highly plastic, black, silty adobe clay. It's a CL. And this stuff up in here, the PIs up in here are all 55 to 85. They're big time. And you don't want to build anything on here unless you put a whole lot of water on this thing for a couple months and get it to suck up all the water it can and swell up and then build something on it. Now you have here is hardpan. There's the hardpan. This is the caliche layer. This is the carbonate. Now as the water percolated through here and it fed the grass was green during the wet season, And it stops raining about the middle of April, and it doesn't start raining again till mid-October to mid-November. So you have 6-7 months, no rain, none, zero, zilch. That's California. Now around here, if you don't have rain for 2 weeks, it's a drought. They're starting to call the president and trying to get a declaration and everything, because and the ground does start cracking and everything. But it's nothing like what you have out west of the 100th meridian in terms of a seasonal drought that's just constant. So that's why you don't do agriculture out here without dams, canals, and irrigation, or wells and irrigation. But these carbonate nodules here have formed over thousands and thousands of years because this ground the water is being cooked off by the very high heat in the summertime. Now, we always get into arguments. How deep do desiccation cracks go? I mean, desiccation cracks are when you have the clay shrinking. We're going to talk a lot about that later. Clay is like a wife. It has a great memory. It remembers everything that's ever been done to it. So clay is the great, you can't take enough classes on clay mineralogy. Everyone you can scam out, go take it, because you're going to use it somewhere down the road. So these materials are really, we say, well, how deep is the desiccation cracks? Most engineers will say, well, I'm going to assume 30 inches. You take a meter stick out there, which is 39.4, and you just drop it right down, and it disappears. You go, oh, it looks like a little deeper than 3 inches. Well, I can't design it for 12 feet. How deep are these things? Well, there's actually documented cases in the San Joaquin Delta back in 1880 by John LeConte, professor of geology at Berkeley, where they did a big excavation out there in these peaty islands, and they actually had these desiccation fractures filled with sand that went down 60, 80 feet. And some of those we think are due to liquefaction features now. We don't know. We don't think they're desiccation all the way down. They're probably liquefaction. But obviously, these things can go a lot deeper than 30 inches. Now, slope creep is something you really need to be aware of, especially if you're a geologist. Because geologists go out in the field at places like this, and they take a strike and dip right here, and then they project it with a ruler. And they go, there's the strike and dip. Wrong. There's no reliable strike and dip you can take on a slope. See why? This is published back in 1938. Because of slope creep. Creep is an engineering term. It means strain under sustained load. All slopes are subject to creep. Creep is the hardest thing to design a retaining wall for. Why? Because you're going to get passive pressures on the active side of the retaining wall. Nobody wants to do that one. Nobody wants to do that one. Come on. No, you don't believe me? Walk around Rolla. Look at our retaining walls. If you find one over 6 feet high that isn't failed, come see me. I got $5 for you. Okay? They're all failed. What's going on? Most of them don't have enough drainage. They put native soil behind them. You're going to go 6 feet with clay, with no drainage. Yeah, it's going to be hard to do long term because of creep. It's going to be hard to do. You also have surcharging if you have load on top of it. But if you go out and what I want you to do, if nothing else you get out of my course, you say, Roger's got a lot of sick jokes, he's kind of, blah, 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 but I want you to become an astute observer of nature. It doesn't matter what I say. It doesn't matter actually what the lab data even says. Don't get overly enamored with lab data. Lab data used to drive me nuts in all the forensic consultations Rogers Pacific worked on. Why? I'll tell you why. You want to have some fun? Take any job you want. Take samples, all the same samples, and then send them to 16 different soil labs or environmental labs for water samples and see the answers you get. It will scare the hell out of you. Does anybody know what they're doing in these labs? Maybe. A few. I would trust Rick Stevenson. There's one guy that does know his lab stuff. But there aren't very many guys like him around anymore. Most everybody have become computer jocks. And the NSF has this new program. It's an interactive soil mechanics laboratory. So you don't have to teach soil mechanics laboratory, because who wants to do that? Well, there's no research money in that. So we have this thing that they had a professor up at Idaho. And I was one of the beta users they sent it out to and said, Professor Rogers, since you had private practice, you're one of those kind of people. could you please comment on Professor so-and-so's program? Oh, yeah. I never have seen triaxial tests that perfect. Just perfect. Oh, gosh, they were like Venus de Milo. Oh, just perfect. Everything just, oh. That's not real world at all. That's some PhD pinhead up in Idaho doing that. That's someone who hasn't run very many triaxial tests. I never had them look that nice. You have to doctor them and do other things, and there's error that gets caught in the lines. They ain't that easy to do, kids. Dynamic triaxial tests, run. You don't want to do those. Those take you a year and a half to figure out how to do them correctly. There's so many things that can go wrong. Do we have those kind of people running soils labs? Not generally. You're lucky, in soils labs, mostly people holding, green cards and at the lower end of the pay scale, and you're not going to get that kind of control. That's why you have to have quality control. You need an old fart like Stevenson looking at the data going, that don't look right. That's right. Doesn't look right. Doesn't look right, guess what? Probably isn't right. But I've seen more trouble with lab data. So why am I telling you this? Well, because I want you to become an astute observer of nature. Nature and behavior are more important than lab data. You go out, you're driving down the highway, and you notice the telephone pole is leaning, Bob. I wonder if it was built that way. Probably not. Probably was built this way originally, but it's leaned over. Oh, that's interesting. Now, this one you got to be real careful about because the amount of tilt here is not an indication of the annual creep rate averaged out. It has to do with the bending moment and how deep this thing is and the fulcrum you have going there. But you'll see things like butt-bowed trees. Those are easy to back out. What do you mean easy, Rogers? Well, they're easy. You can actually, go get a Black & Decker drill. You can get the little coring thing, drill a little tiny 1/8 inch diameter hole, get the age of the tree like that. Doesn't take half an hour. And then from the age of the tree and dropping a plumb line right down this, measure the offset, and get some idea of the superficial creep. Now here again, you have to apply the depth of the rooted zone. You got to know something about botany. I had a tree expert that I used on lots and lots of my consultations. I learned stuff from him every year we engaged him. I learned new things. It was very valuable to spend the money. And so butt-bowed trees are an indication. Things like redwood trees. A redwood tree, it will be 368 feet high, and the root mat is never greater than 2 meters down. And it goes out, like that around the drip line of the tree. And a typical redwood tree will have 30,000 square feet of root cilia area. So it's out there sucking in 30,000 square feet. And it also absorbs water from the atmosphere, from coastal fog in the summertime. That's how they grow so big. So you want to be looking at all these different things. You want to be looking at old retaining walls. This is an old marble orchard. That's a headstone. And old fences, old roads, railroad right-of-ways. You want to look at all these things and just say, hey, how are these doing? How much have they moved since they were originally built? That's a good place to take a little short, take a bathroom break. We got, it's right, 5 o'clock, so I'm going to take a free 4-minute break right now. If you want to go to the restroom, you can. We'll try and break it. Each week, you want to be doing some of the homework, because there's about 10 week, 12 weeks worth of homework there. If you run into some sort of problem, you can always write to me. You just treat me like I'm your boss at work. And everything's going to get down to trust. That's what it all gets down to. So if you want to blow off my work and put it off a little longer because you got some other project you're working on that's really hot, that's fine. You just give me a promissory note. Promissory note says, "Dear Professor Rogers, I have this, this, and this going on in my life. I won't be able to get to this until, but I think I can get it to you sometime between September 6th and September 14th. Great. Better not be past September 14th, or you got to send me another promissory note. Okay? But basically what bosses do, bosses figure out real quick, by the way, who produces and who doesn't. It isn't hard to figure out. And you get about 3 chances, 3 or 4 chances. If you say, "Tony, where's the report?" "Oh, I'll get it to you by Tuesday." "When on Tuesday?" 10 a.m. 10 a.m. comes and goes. Boss is going to be in there. What is he going to think? "Why are you lying to me, Tony? You didn't get it done." "Well, I ran into this and this and this and that." "Well, then you should have been here all night last night." "Really?" "Yeah. It was that way when I worked at the Pentagon." People who get above 05 in the military, people who work long hours, work weekends. Most of the admirals I worked for worked 7 days a week. They didn't even take off on Sunday. That's why they were the admirals. They just worked harder. So what you want to do is develop trust. You want to develop trust with me. I will work with you on anything. I'm a very compassionate person, but don't lie to me. And the reason I say that, that's how bosses are. Once a boss felt you lied to him, you went to the Cardinals game instead of really being sick, you're host. You're going to have a hard time buying back a lie, whether it's your marriage or it's your kids or it's a job. Just don't do it. Do not do it. It isn't worth it. You think people don't like going to ball games? Yeah, we all do. I mean, just be honest. You're always going to be better off being honest in the long run. So we'll be talking more about that later as we go on. So I am flexible, but you got to print it out. You got to staple it. You got to give it to me. And if it doesn't have a name on it, it's not going to get credit. The name's got to be legible. That's the most important thing, is the name. Now, what do I look for? I look for the same thing your employer is going to look for. What's that? Attitude. Attitude is everything. Don't BS me with big, long, flowery answers. Nobody reads big, long, flowery answers. When I did big, huge reports for clients, you know what I always had to do? I had to have a 1-page summary, because that's what the client read. Who reads all the rest of that stuff? The attorneys suing you, and they're experts. That's who reads all the rest of the stuff, to try and find all the little errors and things. Your client just wants to know, what's the bottom line? It's like a husband. Husband doesn't want to listen to his wife tell, what happened today, honey? Well, since the beginning of time, woman has been trying, she gives you this big, you're sitting there going, can we get to the punchline? No, you go, I feel your pain, It's nice about iPod. You can actually have an iPod in over here. Sometimes she doesn't know it. So. Really? Anyway, the boss just wants to know, your clients just wants to know the bottom line. What's the answer? So if I did a real big report, like once we did the largest landslide in the San Francisco Bay Area history, 20 million cubic meter landslide, 1.5 miles long, crashed down into all these Silicon Valley executives' homes. Well, I had a 3-volume report, it was like this thick, $270,000, stuff. But then I had an executive summary with 10 classy, 12 classy color figures, like a press release thing on the top. And that's what everybody took and used. They don't care about all the rest of it. What's the bottom line here? What do I have to worry about? What's the neatest thing I can put in there that tells a story? So when you're doing something that's high visibility, you want to try and tell the story with figures. That's what your clients are going to look at. They're going to look at your figures. So when I'm looking at you turn something into me, I'm going to look to see effort, neatness, and how succinct can you be. I don't want long answers. I don't want answers longer than 3 sentences. So don't try and impress me with long answers. That doesn't mean anything to me. That was back in high school, your high school composition stuff. In the real world, short answers. I'm not asking you anything that requires more than short answers. All right. It's basic stuff. We're not trying to fool you. We're not trying to hide the peanut under the hat. It's basic stuff. If you come and show up, put in an effort, you should get an A. Okay, weakest materials are seldom visible from the ground surface. This is a great picture of that. What do I see on the ground surface? I see the most resistant materials, the sandstone. So we call this slope a sandstone slope. And a lot of geologists will come out here, run across this thing, dang, 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 get some fossils, and they'll call it a sandstone. You get in there with a backhoe and go, hey! That's not sandstone. There's only a little bit of sandstone. That's the ledge rock that's creating the ridge, and there's all this stuff down here. What is this? HIV? No, it's shale. It's worse than HIV. Shale. Shale is bad doo-doo. All the world's geotechnical problems usually revolve around shales. Okay? That's why you need to take clay mineralogy. Shales have all kinds of characteristics. One of the worst is amount of weathering. If I have this protective cover on the shale right here, this colluvium, this slope wash right here, this protective covering will prevent this shale from continuing to ravel and swell outward. Because swell is a function of normal effective stress. The more dead load I put on a swelling shale, the less trouble it gives me. That's why when I go to build an interstate, I put down 4 feet of rock. I don't put that there for drainage. I don't put that there to be the sub-base for the highway. I put it there to be dead weight to hold the frickin' shale down. It's just dead weight to hold it down. A lot of geotechnical engineers don't understand that, believe it or not. They got through school somehow and didn't get that part. You know? So it's not there for bearing. It's there to hold it down. So here, you could be doing fine here, and then when you come in here and you clean this slope off, you take away this protective covering, and you're going to start having trouble right here. And this is a real big problem in places like Cincinnati, where they have lots of this kind of geology. Interbedded limestone, shales, and sand stringers. Sandstones are actually pretty thin. Limestones are pretty thick. But the shale controls everything. All right. Small amounts of iron can color soil horizons. So here we are in the Sierra foothills. And we're looking at here is Merton Formation. It's about 9 million years old. That's what this MYBP, million years before present. That's what that means. It's a geology thing. Geologists sometimes just put that as MA today. MA means millions of years before present. K, little a, means thousands of years before present. So 11,000 or 11 Ka is the Pleistocene-Holocene transition, which came on about 11,000 years ago in temperate North America. The Ice Age actually started ending 14,500 years ago. But in this part of the world, it got here around 11,000 years ago. So it depends where you are, really, where the Pleistocene-Holocene transition is. But here you see just a little, you have a subaerial weathering here with a subhumid environment getting drier and drier over the last 11,000 years. This is 9 million years ago, this material. And so you color it very, very red from all the iron. Very little iron to actually color soil red. Here's a typical, this is at Lyndon Johnson's ranch down in Johnson City, west of Austin, about 90 miles or so, 80, 60 miles. And here you see the red soils east of the A-line, just east of the A-line. I get out to Fredericksburg, about 20, 30 miles west of here, where Admiral Nimitz was from, and boom, I cross the A-line, I don't see red soils anymore. So the red soils go with humidity. They're in eastern Texas. Western Texas is carbonate-rich soils with carbonate nodules, more deserty environment. Here's an adobe-rich A horizon in Walnut Creek, California. That's just east of Berkeley. This area gets about 22 inches of average rainfall. And here you can see the soil horizons, about 30 inches. That's pretty common, even around here in Rolla. The average A horizon thickness around here is about 30 inches. Okay, so 30 inches of highly plastic material. Below that, we're in an argillic B horizon. This is actually the native alluvium right here. See the native alluviums? Pretty nice stuff. The stuff above it has a lot more clay and a lot more reaction. And what you got to watch out for in these areas is pockets, where this drops down and you get a lot more of this bad stuff than you think you had. So what happens over here, this side of the building heaves a lot more than this side of the building over here. And sometimes if you heave a lot more, you break the pipes. You break the pipes, you add more water to the swelling clay, and you're off to the liability races. Doesn't take long. All right, here's actually right here in Missouri, in the upper Merrimack River drainage over near Mansfield. This is by a scout camp. I'm walking up the channel, and I look over here, and I've got a very, very well-developed, sharp contrast between my A horizon and my argillic B horizon. You know, my argillic B horizon, you can actually see all this red. See that pinkish tinge? Those are the clays that are forming in river terrace gravels. Terrace gravels. And this stuff above them here is completely gone to clay. It's been there a long time. You can see things in here like gopher holes and burrows and stuff like that, which helps get water and aeration in there. That's pretty typical of a non-glaciated area. If we were in a glaciated area, this would all be blown out of here. You don't see stuff like this north of the Ohio River or north of the Missouri River, except in the Wisconsin dells. The area got unglaciated. Here we are in the Ozarks. This is over by the Tom Sauk Dam failure, about 90 miles east-southeast of here. And we have here the Bonne Terre, dolomite, and you can see we have a very, very old colluvium up here that has a very nice rooted A horizon. This colluvium's been there a long, long time, way longer than the Holocene. This, I don't know how old this is, but it's really old. But now watch, you do a boring right here, come down, bang, you hit bedrock. Might as well stop, Frank, right? Go another 6 feet. What's this? What's going on here? Old, ancient Native American subway system? What is that? Huh? That's a filled cavern. That's a filled cavern. Got all filled up. See that? All filled in. And so we keep going, and then we get into more bedrock down here. Now, these things, unfortunately, that's about as simple a depiction as I can get for you. In reality, it's hideously more complicated, because caverns are the worst three-dimensional concavity structures on the planet. So when you're dealing in karst, which we are, 22% of the United States is on karst. What does that mean? That's weathered carbonate rock. There's nothing more treacherous for foundations than building on karst. How many borings do you need? As many as you can get. When they were doing Disney World down there, to give you an idea, that's all karst. You know, it's Florida's karst everywhere. How many borings did Dames and Moore's Los Angeles office do down there? Each building had about 600 borings. 600? They Swiss cheesed it, yeah, because they had so many sinkholes. They had to know where the sinkholes were. They had to mitigate all the sinkholes, put in huge mat foundations. They were some of the most expensive foundations in the country back when that stuff was built, back in the 1970s. So here is the other problem. We're going to look in the other direction now. And I was just showing you this stuff right up in here, exposed in the bank by the Tom Sauk Dam flood. Now I'm going to turn and look, and you can see these cavities sitting in here. This is a joint line that's running along here. Here's a close-up of another joint line right in here. And you can see if you drilled a hole right down in through this thing, you wouldn't get any rock. You just keep right on going because you're drilling right down the joint. That'd be right. Same thing right here. You're drilling right there, drilling right along these parallel joints. So in here you have actually some demo cell structures. You actually have a bed in here that was more solutioned than the dolomite here. So this is a pure limestone. It's just gone. And you can see here, if you were building a dam on this, which they built try to build a lot of dams on things like this, like Merrimack Dam, which is on my website. If you want to read about it. You get in here and you just start injecting grout. And it's a grout contractor's pension plan. You never get done injecting grout in that kind of a foundation. It's just bad news. So let's go back one, excuse me. We call that residuum or residual soils. Residual soils have weathered in place, and they're can be very, very complex. And you really can't appreciate them till you gut out the site in 3 dimensions like this, done by the flood, and you can look at all of it, and you're going to go, that's pretty complex. Yeah, very complex. So best thing to use in karst is geophysics. Geophysics is going to identify your anomalies. We call those hot spots. And so you go, well, I got something going on here. I don't know exactly what. I got something going on over here. And something. Those are old sinkholes. Those are old fissures. So geophysics, by far, is the way to go to start with if you're putzing around in karst. Okay, big picture view, looking down. The geomorphic setting. Geomorphic setting is the lay of the land. And you can see here, if we look at a geomorphic setting, down here is the floodplain along the active river. This is the bottom land. This is where everybody wants to buy in the old days. This is the expensive land because it has the rich nutrients in the soil. And when they first got to places like Virginia, and they got to something called the fall line, which is, if you go to Washington, D.C., it's just below the fall line. There's the fall, the Great Falls of the Potomac, where this granite outcrop, and the river drops about 12, 14 feet. That fall line runs all the way along the east coast. And downstream of it, you have these very, very fertile river valleys. And when you get up above it, you get elevated uplands. And those lower valleys were very, very fertile soils, but they planted tobacco. Tobacco was the cash crop back in the 16th and 17th, 18th centuries. And they found that tobacco actually releases a very, very acidic enzyme. And so it leached the soil of all of its nitrogen, the nitrates, very, very rapidly. So after, every year you grew tobacco, the tobacco crop would get more stunted, and finally, 7 years out, you were done. The land couldn't grow tobacco anymore. So what do? You move west and plow new land, grow more tobacco. So here, geologically, we have the most youthful soils going up this valley. And as we get around the corner over here, we get other things. So that's the alluvial. We have alluvial and debris fans. You can see, let me look on here, what they've called alluvial and debris fans. Okay, right here, they're calling this little debris fan. You see these all over the place along the Mississippi and the Missouri rivers, any of the major river valleys where you have tributaries feeding along, coming in. Right down here, you're going to get a youthful fan, and you're going to have to be real careful right in there because that's a different soil condition from the materials right around it. Different soil conditions. So you got to consider where you are. Terzaghi wrote about these things in his first book. His first book that he wrote, or second book that he wrote, his first book was Erdbaum Mechanic in 1925, which is soil mechanics. His second book was Engineering Geology, because he recognized the engineering, the geomorphology controlled everything at a site. You have to study that. So number 3 is upland waterways, right here. These are just these rivulets that come down off the uplands, fairly short time to concentration, high runoff coefficient, depending on the antecedent moisture. 4 is locally depressed areas. Now we have these all over northern St. Louis area, northern St. Louis County. These are upland areas that have old sinkholes and highly developed karst profile. And these are the kind of areas you got to be real careful in when you're siting things and how you're draining things. One of the big problems we've had with highways, we can run the highways along the ridges. That's what we like to do in Missouri. We always ran the highways along the ridges because that's where the best foundations are. And you don't have to worry about sinkholes and drainage and getting stuck so much. The problem with that is if you run the highway along here and you have a lot of impervious surface, every few hundred meters you got to do what? Culvert or some kind of drain. So you have an unnatural concentration of flow going off over here somewhere. And what you find in like Tennessee DOT, Missouri DOT, all of our triggered sinkholes are right next to the highways because we have all this water going over, and suddenly we have 4 or 5 times as much water percolating into the ground here than we had prior to the highway. So the highway development is the trigger for that formation of that sinkhole. So the farmer who owns a sinkhole calls an attorney, his son-in-law sometime, and they sue the Department of Transportation saying, but not for your public improvement for that highway over there. I wouldn't have this big loss of pasture here. That's true. So they've tried to tighten up the laws on a lot of this stuff, saying, well, If you get sinkholes, too bad, you know. Go somewhere else. So hillsides subject to mass wasting, that means landslides. So any hillside can be subject to mass wasting, just depending where it is. A lot of times we put houses in places like this, and then we put septic leach fields out here, and we can actually flush ourselves down the hill gradually by adding a lot more antecedent moisture, so that when the storms come, it magnifies the impact of the storms. And then we have deep, well-drained soils, that's not well-framed, but well-drained soils that develop on the ridges. And that's why we see the highways going up the ridges. And you see that around here. Here's a real typical weathering profile in glaciated areas north of the Ohio and Missouri rivers. This one's actually in Ohio, I've picked here. And this is pretty typical. We have a sequence of limestone beds intermingled with some shales. And you go up here to the top of the picture and you actually see there's some wet zone right here. We have a very immature, thin, immature soil horizon because the soils that were there got carried off by the glaciers. So the soils are gone. It's a completely different geology from down in Kentucky. And so we also have a permeability boundary along here because of the soil creep, rock creep zone, the hillside creep zone. Causes the materials to dilate. They have a higher hydraulic conductivity, so you get a lot of moisture that weeps out of this area, and you get a little underplucking going along right here. Now, if you look at this cut, one of the first things you notice is absence of vegetation. I mean, we're in an area here that has, 55 inches of rain a year. I mean, most of this all summertime. Why isn't stuff growing on this slope? That's one of the questions you want to ask. That's one of the things I want to teach you to do. That's becoming an astute observer of nature. You want to look at this slope and say, nothing growing on this one. Now, they took me out here to look at this one because they were having problems with it all along the thing. Now, there were other slopes along here, similar geology. They weren't having these problems. But I want you to notice something right away. Number one, what's going on right here? What is this called? Talus. Talus. That's a scree slope. That's a talus slope. Where's that stuff coming from? Is it young? Recent? Yeah, it's yesterday. It's very recent, geologically speaking. What's going on up here? That's where talus come from. Talus go down to here. So you have a zone that's very actively bloop, bloop, bloop. What's causing the blooping? Come on. What's causing it?
The rainfall?
Yeah, water, percolating water. It's not the rainfall, it's the percolating water where you have emergent seepage pressure. The emergent seepage pressure, when you get a lot, you get a lot of rain, like over a period of days, a lot of water seeping down, that is raising the pore pressure enough that you reduce the effective stress and the blocks are falling off. So one block at a time. It's not all happening all at once, but it's just constantly going to be coming off there. So if you wanted to arrest that problem, there's several things you could do. One, you could just shave this top of this slope back, shave it back more like a natural slope so that the water would come out gradually, not all at one place. Or you could put a drain of some sort in up there. That'd be a little more iffy, a little more difficult to do. But a lot of times you're on highway, you're down here, and as soon as you get more than about 12 feet above the road, your options really start getting thin because it gets expensive. Anything you do to fix a highway, you want to do it on the highway and on the shoulders if you can. As soon as you start going down the slope or up the slope, the cost is going to go out through the roof. When I get up on a slope, that's going to cost me 4 or 5 times as much per yard to putz around up there. So if I had to attack something like this, what I would do, I would actually build a rock ramp here. And I would ramp up, get my equipment up 18 feet above the road, and then work off that, that temporary platform, put my soil nails, my tiebacks, whatever I want to put in. And then I'd take out that rock wall, make it out of gabions, something that's, nearly vertical. Okay. Contrast between effluent and influent stream systems. In the Ozarks, we have a lot of influent stream systems. They're called losing streams. Dry Fork, which I live right along over here, is an influent stream. That means it loses its water pretty quickly. I mean, I have water on both sides of my backyard. It's wonderful. When it's been raining, you hear all this gurgling and rapids going and everything. It's all over in 2 days. And 7 days later, there's no water. About 7 days is the tail, because I'm at the upper end of the watershed. So these are losing streams, and they're pretty common when you're in karst areas. Karst areas have losing streams. When you're in a typical area with a typical kind of non-carbonate kind of stratigraphy, you're going to have typically an effluent stream. So you're going to actually have a water table up here. That water table fluctuates by decade and by year and season. And then you could have some springs once in a while. Typically, there's seasonal springs. And then you're actually going to have some feeding. You're going to have this phreatic surface, the saturated zone, that comes down and makes connection and is coincident with a perennial stream. Perennial stream. Now, a lot of times you have a big stream like Shenandoah River. It gets about 10% of its inflow from percolation like this. That's a typical number, 10%. That's back in Virginia, places like that. Around here, we have both systems, although we're dominated by this one. This one's really big time when you get down to Kabul and that area, West Plains. You don't see any channels down there with water in it. Everything, you just see big sinkholes all over the place. They're like big bomb craters. And so effluent systems, really typical east of the 100th meridian. All right. Undulating contacts. This is probably the most important picture I'm going to show you, and it's not a very exciting picture. It kind of looks like a, barf or something? I don't know. Pretty nondescript. What I'm looking at here is a quarry face, and it's an old quarry. Now, one of the things I learned in California, you're going to go out and give people bids and plans, bids and spec, in 72 hours. You better find out where all the old quarries are. Now, in Phelps County, we got 3 active quarries, and we got 16 derelict quarries. You want to know where the 16 are, because if you got a derelict quarry just down around the corner from some big problem, that means I can go put in a little small crusher, system, or just I can just put in a skimmer, put in a screen, and I can actually go out there and for very little money get my rock. Because all the money in aggregate, folks, is transport. You have a price per ton, 1.2 tons per cubic yard, FOB. What does FOB mean? Come on. Anybody from the working world? FOB is freight on board. That's the price they charge you at the quarry. What do you pay for it over here at your house? 64, 74, 84, 94. Whoa. How much are they charging over here? 1.2 tons per cubic yard, and they're charging it by the ton, and they're going to charge you $6, $7, $8 a ton. How come you're paying $68 a ton over there? Because of transportation costs. Diesel. Got to bring it over here and drop it. Okay? So all the money is how far you got to go with it. So if I'm going to use rock gabions, for instance, I'm going to use gabions every time if I'm within 3 miles of a quarry, because it's going to be cheaper. Because everything gets down to transportation costs. Concrete, steel, gravel. Gravel's cheap. So if you make a repair out of gravel or crushed rock, crushed 2x3, you're going to do it. Because you're going to get drainage, and you don't have to worry about compaction. You can do it in the middle of the night. You can do it without, raining. Doesn't matter. So you want to know where all the quarries are. So I'm always out scamming all the quarries, looking at all the quarries. So when we look at a quarry, here's a typical quarry face. And I'm looking at a rock here, and this is all the same rock. So I go get the geologist, I say, Mr. Geologist, tell me what kind of rock I have. So he come out here and he goes, you have a glaucophane, micaceous greenstone. Oh, really? Glaucophane, micaceous greenstone. Okay, great. Yes, he's going to give it to you in descending order of mineralogical content. Very, very useful for nothing in engineering, but we know what the petrology is that way. Okay, that's good. Okay, so why is this stuff red and this stuff is blue? And the geologist will tell you, this stuff is oxidized and weathered. This stuff is not. What does that mean to an engineer? That's engineering terms now. I'm going right brain, left brain. You like this? I'm switch hitting on you. Okay? So, oxygenated groundwater, non-oxygenated groundwater or no groundwater. More engineering stuff. Crappy material, lots of fines, can't use as engineered fill. A lot of times because more than 30% passing the 200. That's the engineered fill spec in all the DOT books. This stuff you can use. So this becomes what we call in the mining industry. What do we call this stuff? Burden. It's like an old boyfriend. Burden. Burden. Meaning you got to cut this stuff out of here, and you got to pay money to move it over here and get rid of it. It's waste. Now you can use waste dump material sometimes for stuff, but this is real typical of what you see in quarries. Go to some quarries, go to some road cuts, and start looking. I want you to get the Mark 1 eyeball. You're going to have an assignment. We got to go out and make some observations. This is the kind of stuff I want you to observe. This is wild. So, now what would happen here? I send out the geotechnical engineer with a PhD from MS&T. The name, the degree, the difference. And he drills a hole right here. And he drills a hole right over here. What's the cross-section look like? Two completely different materials with a line between them going, don't know what's going on. Yeah, welcome to the real world. That's the real world. Highly undulating contact. Highly undulating, which is a big college term for moves all over the place. Okay? All right. Here's another view. Interstate 5, coming down to the Klamath River crossing, north of about 5 miles north of Wairika. And we're seeing a greenstone here cut about 200 feet high for a 4-lane interstate highway. This material is the exact same material as this material. This is just the weathered zone. Now that weathered zone is about 50, 60 feet thick. Now, look at this. That's the contact. Watch. You got some material here that's really resisted weathering right in the middle of that zone. But what's happening here is water is raining on this slope and percolating through and coming down through this stuff, and you're having oxidation. You're having cation exchange. This material is different material. It has a much higher permeability, and it has a lower strength. And you're going to have a lot more fines in it. You're going to have a much easier time excavating this greenstone, weathered greenstone, than you are excavating this greenstone. And that's the kind of stuff we try to put in all our bids and spec packages. Well, how do you delineate between these things, Dr. Rogers? Shear wave velocity, usually. We use shear wave velocity for excavatability. We cover that in the 441 class. So we go get all the old Caterpillar tractor handbooks, going back to handbook number 1. I think we're on 47 now, 44, 45 in there. And they have the shear wave velocity versus ripability for different kinds of equipment. And of course, CAT always wants you to buy the biggest, most expensive equipment. So you can't use this year or last year's CAT handbook if you got a D8. You got to get back to 1977, use a D8H. So you have to have the old book to see if you can rip it or not. But the ripability is really important in a situation like this. So the ripability of this material and that material, you're going to get paid 4 or 5 times as much to remove this material as you are that material. And this material is going to be an order of magnitude higher permeability, or 2 orders of magnitude, than that material. Because that material, the joints in this stuff are all cemented by calcite. So that's why it's not getting weathered. Cemented by calcite, and it's in the rain shadow. Doesn't get enough water. Okay, here's another case. This is actually over in, I'm in the snowy mountains of Australia in this particular picture. And I have, I'm in granites here. And you can see how things get boogered up here by the creep zone up on top. And then this is a pegmatite dike in the granite, much more porous. And so I have more of the feldspar staining in here. The orthoclase is being converted to the salmon-colored microcline feldspar. And you can see here a very definite zone right in here where it's more weathered. And then you have these little stringers here and there, especially along joints where you have more water. Water travels through the joints, and so you're going to get a little more weathering along there, a little less strength. Now, you can have healing of joints, especially by iron, that makes them stronger. That's like injecting superglue. But that's the minority. Most of the time, the process of fluids running through there actually weakens it instead of strengthening it, but not always. Okay, here we are in Hawaii. This is a fairly recent highway cut for the Wilson Tunnel, done back in the late 50s, early 60s. And if you look at this same cut today, you can't see anything. It's just covered with jungle. But this is looking at the Ko'olau volcanics, and they got some of these big joint surfaces here. Here's a big joint surface. You see where they had a planar failure here. But as we go up towards the original hillside, we can see we have an undulating series here with the weathering. And this material up here, you can see these little shallow pop-outs that have been occurring right in here. This material is much more weathered. There's another one where they have a pop-out, come out eroding here, than the material down here. So it's all the same material. It's all the same Ko'olau volcanics, but the porosity impacts the weathering. Now, volcanic rocks are extremely porous. They are just filled with joints, ubiquitous jointing, because they shrink so much as they cool, and they cool very, very rapidly. And so you get lots and lots of joints. You don't want to build dams on volcanic rocks. Just don't go there. It's like building dams on karst. You can do it, but your brother-in-law better be the grout contractor, and you're getting a kickback from him, because you're going to do a lot of grouting. All right. 5:44 p.m. And we're going to start on rock joints. Rock joints, specific surface area, and weathering. Here I am in a place called North Canyon. That's a tributary in Marble Canyon, Upper Grand Canyon. I'm in the Esplanade Sandstone. It's a Pennsylvanian age member. It's a quartz arenite. Look at how prolifically jointed this rock is. I want to tell you something. That's the strongest sandstone in the Grand Canyon. What? The strongest sandstone has the most cracks in it? Yep. Yep, it does. Because it's got very low strain threshold. Okay, it's not mushy. So this stuff has been excavated by a natural channel, and it's exfoliating. And no, you don't just get exfoliation in granitic rocks. That's another, fairy tale that we get in some of the physical geology books. All rock is jointed media. This shows the orthogonal joining in a layered sedimentary strata, and groundwater travels down these preferential paths. So groundwater, in this case, I'm flying over the Green River Canyon near Green River, Utah, and what's going on here is groundwater has flowed down these regional systematic joints, and it's solutioned out these corridors, these preferential flow corridors. So you have weathering and disintegration, and it's enlarging those flow conduits that are sitting there. And you can see any of these things in remote sensing data. You get remote sensing data in a semi-arid area. It's very easy to see the near vertical joint suites. They're not hard to pick out. Now here we are on the ground, and so we got another view here. We're on the ground. We're near Colorado City, Arizona, along Short Creek, and we're actually looking at the Navajo sandstone. That's a Jurassic unit. It's about 2,300 feet thick in this part of Arizona, Utah. We're right near the Arizona-Utah state line right here. Utah's just to the right here, out of that way, out of the picture. Okay. So we're looking at here, these are joint faces. This is a shear joint face. Most of the time when you go to a place like, this is just south of Zion National Park, when you go to places like Zion or Yosemite or Rocky Mountain National Park, Glacier National Park, what you're usually seeing are joint faces. These are huge regional systematic joints. So they have very regular geometries. Right here you see one joint going down, big huge face, and right over here is the joint that's almost 90 degrees to that, believe it or not, going this way. This one's going that way. And What you're seeing here is a very unusual in that this is a face that's transverse to both joint sets. So what I'm seeing here is thousands and thousands of 2,000-foot high joints, and they're actually crisscrossing one another like this. Cross. And so what you see here, I want to get through to you, is all massive rock is jointed, and fluid flow goes through the joints. When I first started serving as a consultant to EPA years ago, I didn't want to have anything to do with the geo-environmental industry. It just isn't sexy to me. It's not like doing the combat engineering I do on sliding highways into the Pacific Ocean and stuff. But I got roped into it through a friend who was doing Lawrence Livermore National Lab, and they were having all these problems. And so I started becoming a technical referee on these very difficult lawsuit cases that the EPA had on landfills, especially like places like Texas. And you had these guys, they were soil mechanics people with no background in geology or rock mechanics, and they're going out into sites like this and drilling vertical holes and then saying there's no leachate leaking out because they didn't encounter any leachate in their vertical hole. Now, kids, here's a joint surface. Here's a joint surface. All the fluids go along the joints. If you drill a hole right here, you're never going to see them. Vertical holes in vertically jointed rock is the work of a moron. Shouldn't even have a PE license. That's stupid. That's wasting your client's money. Horrendously wasting. I wrote some stuff like that. That's why I had to move to Missouri. And people wanted to kill me. No, I'm not kidding. What do you do in a case like this? You have to do angled holes. You're going to mess around with trying to find dense, non-aqueous phase, liquids who are sliding down the joint surface. You got to do angled holes so that you pierce all the joints, or you pierce some of them at least. Do an angled hole, 15 degrees, go through, and then do your sampling. Now, as soon as we made these applicants, do that, everything changed. It's pretty sad. So you had an industry there that was just expanding so rapidly, they weren't bringing along the right kind of expertise. That's why you have to have third-party peer professional review. Here's a step cut in volcanic strata that illustrates some of the problems in raveling that are real typical on highway cuts, or any kind of cut for that matter. Most of the weathering is going to be in the upper part of the cut. This is where all the action's going to be. This is where everything goes wrong, and these materials come down, and they either clog up your bench up here, your drainage bench, or they come sailing down and make it all the way down to the highway. This is the kind of stuff that drives us nuts, because it's very hard ahead of time with a typical geotechnical investigation. It's very hard to come in here and predict how much raveling trouble you're going to get off this thing. You got to realize we get one rock up here that loosens up and comes bouncing down here, and through conservation of momentum, it can come bonk, kabonk, kabonk, right onto the highway. Somebody hits it, and they become a quadriplegic. You're out $20 million paying for their medical bills. Now, we save some money on the slope here by not shaving this back. We save, $30,000. We just lost $10 million in the first accident. So you got to look at what's cost effective. Now, back when they were doing this kind of work in the 60s, they were assuming these cuts had a life of 20 years. That's ridiculous. I mean, you're looking today, 75 years, pretty much a minimum. But we still don't have good numbers on erosion rates and weathering and aging effects. That's the one huge area of geotechnical engineering we're not doing real good on. We can't go out, drill holes in a couple days, take the samples to the lab, run a bunch of tests in the lab, and get the report out all in less than 3 weeks and tell you how the site's going to behave over the next 37 years, 67 years. You can't do that. The only way you can tell that is to get your butt out here and look at the slopes in similar geology, similar hydrology situation to your project site and see how they've done. Everything that I've learned about my business that is really important has come from direct observation and experience. It didn't come from the classroom. It came from going out and looking at slopes like this one, going up here and making some measurements, and going, this is colluvium up here, by the way. This is soil. And they left it in at 1-to-1 cut slope. Soil doesn't stay on a 1-to-1 cut slope unless you can keep the moisture in it, keep some negative pore pressure going, keep it there. And what happens is when the water spills over this thing and it gets saturated, every once in a while, for a couple days, this just comes apart. Just starts flaking out, coming down on them. So it's a big problem. Notice here they did a tree planting program to try and, they thought that, well, if we put some trees in here, then when the rocks come down, that will absorb some of the energy of these rocks coming down. But the trees, you know, pretty hard to plant trees on a slope like this and have them survive. It's basically like, you know, they get cooked like Thanksgiving turkeys. This thing's so hot. You have to plant them on joints. The ones that are right on a joint will get enough water to survive, but that's about it. Well, most of these trees are on the mid-slope drainage terrace that actually survive. They had a very high die-off on this one. Okay, one of the most important slides I'm going to show you is right here. Joints break the rock mass into discrete pieces, and they create a much higher specific surface area. The more fractured my rock is, the closer the fracture spacings, the thinner the beds, the more rapidly it's going to weather and ravel and have chemical ion exchange. Big blocks take a lot longer period of time to react because they have less specific surface area. Okay, so you don't have to be a rocket scientist to understand that one. Here is a typical plot showing the asymptotic relationship between the number of particles, see over here on the y-axis, and the total surface area. And you can see here this thing's just taken off. Big surface area means much more chemical reaction for chemical weathering. And it also means much smaller pieces for wedging, like ice wedging and mechanical weathering. So it gets you both ways. So units that are more thinly bedded, like shales, are always the problem. Now here's a case where we're near Olmsted Point, Yosemite. We got a WPA highway here. Actually, it's a Civilian Conservation Corps highway. And we have some joint clusters. Right, here's a joint cluster. And a joint cluster is where you have a whole series of joints right next to each other. And so you have very high specific surface area in these blocks, maybe an inch thick, between the joints. So you get a lot more moisture running through here as compared to here or here. And so what happens here is after they cut this cut for the highway, which is about 22 feet high, and you got another joint suite here and right there. And after they cut the highway, they, of course, plow it for a while before they close it all down, and then they throw the snow up, and that thrown snow up here creates insulation. And what happens is they get pore pressure buildup in here, and the thing blew out on them and actually caused some problems with the traffic. And we actually, when they were doing the Helms pumped hydro projects, Pacific Gas and Electric, 1977, 78 timeframe, they were doing a tunnel and went through one of these things, and they drained an entire mountain. And it was so catastrophic, the amount of water that came in through that joint cluster, that everybody in the tunnel tried to get out, and they killed a couple guys through accidents, one of which was a classmate of mine in Berkeley for the master's degree. His first job out of college. He was there 1 year, 11 months actually. He got smashed when one of the guys operating one of the miners, the underground mucking machine, did a Y turn like this and smashed him and then drove out to save himself. Didn't think about saving anybody else, and he just killed my friend. So joint clusters are always going to be filled with porous, low cohesion grus. And that can be pronounced any different way, like lus, los, lurs, grus, grus, gunt. It has all kinds of different pronunciations. Here we are in Grand Canyon, and we're actually walking around here, and these is a Precambrian Zoroaster granite, and we're actually walking right on the joints where the joints have been mineralized with iron. So this is more resistant, and the core rock, the core stone, is actually the pools here. It's been eroded away. So percolating groundwater can also cause cementation along joint systems. And this is a big issue in the basement rocks here in Middle America. You get down in some of the basement rocks like we've encountered in the Washington Metro and places like that, and woo, you come along and hit an ironstone in here, and it stops you. This is like hitting steel. It's really something. So most common cementation agents are carbonate, silica, and iron. Carbonate's very, very soft, hardness of 3. Silica is 7. Iron, 7.5 typically. Iron's bad news. Really hard to cut through. And note the maroon color is the iron oxide, and it's going both directions. So you see the maroon's actually going along here, going in that direction, as well as the joint going in this direction here. So those are orthogonal, regional systematic joints. All right. The precipitation of iron oxide we should always be aware of because this is a much more common when you get to subtropical and tropical, subhumid climates. The chemical reaction involves iron-rich minerals, usually the pyroxene coming out of the things like granites, granitic rocks. And you have pyroxene in the presence of oxygen and water, you're going to get iron oxide. And that iron oxide is an extremely strong binder. It's hematite. It's Fe2O3. And hematite can really give you fits on construction projects for a lot of reasons. And also, if you get it in the concrete aggregate, you're going to get rusting problems too. So it's bad news for that. Here's another picture of that case in Grand Canyon. This buddy of mine is standing on it, marks, and you can see these mineralization halos. Now, what we're showing here is we have an iron-rich halo in the middle, but as you come out, you have other materials that have cemented, that have percolated through these joints and cemented the rock together, and that's a function of the solubility coefficients of those different kinds of salts. So like if you look around Death Valley, California, that's the low point at Badwater is 283 feet below sea level. Well, they had a lake in there. It was almost 700 feet deep, all through the Pleistocene, up till about 7,000 years ago. It dried up. And I went out there when I worked for U.S. Borax. We drilled a hole at Badwater, and we hit 1,000 feet of lacustrine sediments, 2,000 feet of salt, 1,000 feet of lacustrine sediments, green clay silt, and then 2,000 more feet of salt, and we stopped. We're down 2 miles. Just salt, 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 salt. Same kind of geologic structure as the Dead Sea between Jordan and Israel, which is much deeper. It's 1,800 feet below sea level. So what's going on there is you have halos of salts. As that lake shrunk, in case of the Dead Sea, it was called Lake Lisan, Glacial Lake Lisan. As it shrinks, you get the carbonates first, and then you get the halites. And the last thing to come out is the potash. It's the potassium salts. And so they mine those salts in the Dead Sea big time. The whole southern basin of the Dead Sea has all been diked off years ago. They extract potash out of it. Exfoliation in massive rocks. Do you want to take a short break now or just have me stop at 6:20 instead of 6:30? What?
So we can stop later. I'm fine now. What everyone else thinks.
We stop early. Want to stop? Just stop earlier by going on right now. Does anybody want to have a bathroom break? Okay. What I'm going to do then, I'll start moving the bathroom break to like 5:15. Then we'll just have the one. Then we'll try to finish up a little earlier. Okay? Since it's dinner time. Exfoliation in massive rocks. Here's how I got interested in geology. I was always interested in civil engineering because I grew up in a general engineering construction family, earth moving. And so what I was really interested in was rock climbing in the Sierras. I went to Royal Robbins Rock Climbing School here at Yosemite National Park. When I was 17 years old, I spent my entire life savings. My father was furious. So was my mother. My dad was an art, he loved art and fine things in life. My mother was a librarian. And he goes, I pissed away all my college savings. Well, I figured, I'll just, I want to fly jets in the military. I'll just have the military pay for my college. So that's what I did. So I went off to school without. I never took a loan in 10 years of college. I always worked. I was always hustling. In fact, when I was at Berkeley, I had a great business. I actually made more money with this than I did as an engineer for 3 years with a PhD and PE. I had and my dad, my credit to my dad. My dad said, you want to make money, you got to do something people need, but you don't have a bunch of competition in it. So, so what do they need around in the Berkeley Hills? They had poison oak all over the place. And nobody wants to pick weeds or kill poison oak or pull poison oak. Especially America. Americans don't want to do anything dirty, hot, sweaty. So I took those on. I had a poison oak removal service, and I was the only guy in the phone book that had it. I made $60,000 a year while I was in grad school. It's a pretty good deal. Going out there, and you just tech new up, get out there real early, be done by 11, come back the next day, tech new down again. It's not that hard to do. But I wonder if anybody's ever relit that up again. But anyway, it was good money. So I wasted my money to go to rock climbing school. But this is the kind of stuff that I saw. This is Little Shut-Eye Pass in the Sierra Nevada. This is the strongest rock in the Sierra Nevada. We tested it at Berkeley. It was like 34 to 37,000 PSI compressive strength. 10 times stiffer than structural concrete. Notice what strong rocks do. Strong rocks are brittle. Thank you. Brittle. All right, so here we are, backing away. And by the way, if you got really good eyes, that's my Jeep right there. My Jeep CJ5. Not the same one I drive now. I drive a 43. That's a 65. That was my first one, bought when I was 18. But here we are. The Jeep's parked there for scale. And then you're looking at this glacial cirque here in the Mount Gibbons granodiorite. This is a big glacial cirque feature, about 500 feet high. And this thing is just permeated by countless sheet joints. And when you get up close to sheet joints, this is what they look like. This is up in actually the Tenaya drainage in Yosemite. These big, huge sheets, and then they are semi-parallel to the ground surface. Now, these are what drive us nuts with dams. These are tied to probably 50% of the dam failures I worked on all over the world are sheet joints. They didn't take them seriously. They had one in Brazil just a couple of years ago. Brand new roller compacted concrete dam, failed on its first filling because they didn't grout the right abutment, the sheet joints. Here's what they look like up close. So you see here, this is a closer view of the glacial cirque in the Little Shut-Eye Pass. And there's a dam, big dam, right down here in the upper San Joaquin River called Mammoth Pool, where they battled enormous problems with sheet joints. And that was one of Terzagh's last consultations. They did. He wrote a very famous paper on it called Dam Foundation on Sheeted Granite, which appeared in Geotechnics in 1962. But these materials have a low strain tolerance. They're very strong, but low strain tolerance. So here we're moving to the Rocky Mountains, Independence Pass in the Rocky Mountains. This is a glaciated area. So you have a very planar surface here. It's been glaciated. All the soils are gone. See? No soils. You've been glaciated. All the soils have been moved away by the glacier. So man comes in here, does line drilling, makes a highway. What happens here? Well, you get wedge failures. These wedge failures are along valley side joints that form semi-parallel to the ground surface. So this is a real big problem in massive rocks anywhere you go around the world. Here's a drawing I did. It's from my PhD thesis, where we're actually looking at Zion National Park. And we're looking at here is the regional systematic joints cutting through the Navajo sandstone on top the Moanov shale and sandstone. And you get these diagonal valley side joints that are parallel to the trend of this canyon right here. So we got this canyon running up like this. These things, got to do this right. These things are parallel to that. So when you're walking along out here as a geologist, you don't see these things. They're back behind the face. What you have to look for are big hunks like this of drop rock. And you go, what's this big, huge clump of rocks doing here? Well, you look up. There's the face it came off of. And that face is inclined like 60 degrees. It's just perfect for a rock slide. 60 degrees. 45 minus phi over 2. That's why. So there is your clue. Now, how do you go track these things? You go in these little re-entries. You go in these little side canyons, and you get in the side canyon, aha, there you see them. See that? Then you start seeing these features. Now, these are really problematic to deal with for highways and pipelines and dams. Here's one in the Grand Canyon, upper part of Lake Mead. I've been a consultant on Hoover Dam for over 30 years now because I did part of my PhD thesis out there. And this is a Zoroaster granite. These are valley side joints, just a whole bunch of them. Boom, 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 boom. And this whole mountain here slid down, big block slide, coming down on about a 40-degree slope, and went into the river and blocked the river. Had a big landslide dam. And that doesn't last very long geologically. The river builds up behind it, a bunch of silt builds up behind it, and the river just blows the thing out of there. So the dam's debris is all gone, but the scar where this thing came out from, and recently, very geologically, very recent, is there to see. So in this kind of a case, you can actually go up here and see the valley side joints very, very well exposed. But every dam site I've ever worked on in the world has had valley side joints. Every single one. One of the first sites I worked on was Reza Shah Kabir on the Karun River in the Zagros Mountains in Iran. And they had just all sorts of problems with the foundation on that when they got in there and started digging things out. It looked like Tom Sock over here. Oops, we're done? Okay, nope. Sheet joints. Sheet joint exfoliation can form in any massive rock so long as it retains some portion of its original elasticity and is relatively devoid of fractures. What you're seeing in here, my wife actually took this picture too. This is in one of these tributaries in Marble Canyon, and you can actually see these fractures curving up. They're forming in response to the excavation of this side canyon. And we're actually looking down the canyon, and you can actually, the canyon is joint controlled by this master joint set and this one right here. This is a pool of water right here. It's going downstream, and the Colorado River is down there about 300 or 400 feet lower than the picture. So you have these series of joints that are curving around like a big U. They're U-shaped. And that's in the Esplanade sandstone, remember. Now here's the largest one I've ever seen. This is Ayers Rock. It's in central Australia. It's a Arcosic sandstone of Precambrian age. It's about 9 miles long, about a half mile wide. I think it's about 600 feet high. And what's going on here, this is an exfoliated slab that's about 35 feet thick. That's a 3.5-story building. This is an enormous feature. And you can actually see daylight right through this thing because this is buckling. This is Euler buckling. This is actually bowed outward, and you get this gap in here. And these little alcoves down here are where they've had chemical weathering of the Arcos because the old erosion surface used to be right up in here. These used to be buried, and when you're slightly buried, you have condensation of moisture just under the ground surface. This is the same way we got the damage on the Sphinx over in Egypt. The Sphinx was buried, 2/3 buried in sand. You get condensation of moisture in the sand. That moisture then attacks the carbonate in the sandstone, Nubian sandstone, and you get pits out. So when they excavated the Sphinx out, all the part that had been buried prior to the excavation is all pitted out and weathered, chemically weathered. So this one's been under subaerial exposure for millions of years. Western Australia has a ground weathering surface that dates back to the Cretaceous, so past the KT boundary. That's the oldest weathering surface on the planet, is Australia. So that's why we have some of the biggest slabs there. Now here's one where I'm actually floating down the Colorado River, my first trip in '78. I'm rowing along. That was one of my life goals. And I'm looking up here, and I'm actually seeing a big wall arch coming around and curving around. This is a valley side joint again, subparallel, coming up right like this, going right like that, and on up. And we have this wall slab that's pulled out in tension, so you get this circle effect. If I can get in here and show you. I can't. But it's, yeah, I could do it. See, I'd do it like this. Yeah, it's pulled out in tension, and that's why you get the circle on it the way that you do. And that was in limestone. And this is at right near Vasey's Paradise, right down, I can't see. Can I pull this out of there? Yeah, there we go. Mile 32.6. River mile 32.6. Okay. Now here is in a quarry. This is actually at Yosemite National Park. It's in the National Park quarry that was built by the Civilian Conservation Corps back in the 30s. And this actually shows how you have exfoliation joints very close together right near the ground surface. And as you get deeper into the quarry, the spacings get further and further apart. Now the Romans actually made note of that and used that when they were quarrying. You get your bigger blocks from down here, you get your smaller blocks up in here, and you make dimension stone out of it. Nothing new about that. What the Romans would do, they would use fire, and they would use wedges. And remember that guy that came across, Hannibal, and attacked him from Carthage? Well, he came across the Mediterranean, landed to the west of Italy, and then came out through the Alps. And in order to widen the road going through the Alps for the elephants, they set these little fires. Because if you heat rock and then you throw water on it to quench it, you crack it. You exfoliate it through thermal strain. And so thermal strain been around a long time. The Romans used thermal strain with fire and quenching, which they might have learned from the Carthaginians, and they also used wood pegs. So you drill a hole, you put a peg of oak in it, and then you drip water on it. The wood expands, and you force a tensile fracture between the holes. The holes are about 5 inches apart and about 5/8 of an inch in diameter. Here's fire-induced exfoliation. I saw this when I was fighting on fire crew as a teenager in California with the California Department of Forestry. And then I went off and asked my professors at Cal Poly, I said, all my textbooks say that temperature doesn't cause exfoliation. It doesn't cause rock. And they said, that's right, it doesn't, because David Griggs, who's a member of the National Academy of Science and who got the Penrose Medal from Geological Society of America in 1975, he did tests at UCLA, and he was from MIT. And the brightest stars come from places like MIT. Well, Griggs was a consummate scientist, not an engineer. Okay, so I'm going to go left brain on you now. So all you scientists, hang on to your panties. Don't get upset at me. But scientists, typical science, didn't have solid mechanics background. Okay, he's not an engineer. So he takes little discs, he takes cubes of basalt, granite, and limestone. He makes beautiful little cubes out of them. He takes it out here, and he heats it up like a scientist. Heats it up real, real hot. 600 degrees, cools it down. Does it 400 times, nothing happens. So temperature has no effect on rock. And that's in every geology textbook, even the ones used on this campus by our geology department, even my department. What's wrong with that? Put your engineering hat on. What's wrong with that? Does that replicate what goes on in the real world right here? I mean, no, what's going on here? What's going on? There's insulation, isn't there? That block is never going to develop tensile strain if it's free to expand and contract. Expand and contract. But what if you had a long block? Let's say you had a block 2 inches in diameter, went all the way down like this for 25 feet. And I stood up here with a blowtorch and went, heat it up, heat it up, heat it up. What's going on down here? Any thermal strain? You bet your ass. That's just basic solid mechanics. This is going to heat, and what's it going to do? It's going to expand. That's how the guy made Stone Mountain, Georgia. David Griggs probably wasn't out there. He was at Westwood. One guy made Stone Mountain, Georgia. Even if you don't like the Confederacy, but one guy out there with a blowtorch carved that whole thing. The Vietnam veteran went up there and just turned the blowtorch on. And, this is after they took them 30 years to build Mount Rushmore, with chisels and dynamite and all the slow. This guy just took a blowtorch, just started carving. You heat up the granite, real strong granite, you heat it up, it flakes off, it exfoliates. But all the textbooks say heat has no impact. Wow. But they're all been peer refereed and put in journals. So it has to be right. Seal of God. All right. So heat from forest fires and brush fires can cause thermally induced exfoliation. There's nothing new about this. It's in the literature all the way back in 1940. K.O. Emery's work on forest fires down in San Diego County that he observed when he was at La Jolla. This is my own thesis work, some of my thesis work, where I actually took a finite element program and looked at the thermal differential to cause tensile fracture, and it was 9 degrees. I think it was the amount it would do it. And what you see is, if you look at it from a solid mechanics perspective, here's the temperature at the ground surface on the hottest time in the summer, and then going down. By the time we get down to 80 feet, we have a constant temperature, something like 55 degrees Fahrenheit. And so if you look at a thermal model, it would predict fractures increasing in spacing exactly the way we see them in quarries. So they could be thermally induced fractures, could be a lot of it. We also have the release of stored elastic strain energy from unloading, from glaciers, from the mountain itself that could be playing a role. If we actually took that model that I just showed you and we overlay it on data for granite quarries in New England. Here's granite quarries in New England. And we know that they've been unloaded by a mile-deep glaciation over the last 14,000 years. So down here, you can see in the upper 20 feet, the data just match exactly. And then here, this is the temperature influence. And then here, what you're seeing is the glacial unloading influence. You have both factors going on. That's real world. What I was doing was an isolated model, looking at just one thing, temperature. But you got other things going on as well. Okay. Well, we're going to stop there today and try to pick this up, because I think weathering is so important, it may take us a little longer to get through it than I've allotted 2 weeks for it. We'll see how we do. We're going to stop there for tonight. We'll pick up with spheroidal weathering next time.